Helping our children develop their inquiry skills is important and should be planned for, much as we plan for the development of their knowledge and understanding of science concepts. In order for the children to work as successful scientists, they should be taught a wide range of essential inquiry skills. These skills should build upon opportunities for them to play, explore, create and engage in active learning. It's important that there's a progression of skills over year groups and across a year. When this isn't planned for, children could potentially be practicing the same skills over and over again. If they can measure using whole number standard units at age 7, then by age 10 they should be looking at ranges and intervals in their measurements. Likewise, if they're grouping objects at age 5, then by age 7 they should be able to justify their groupings using prior knowledge. When inquiry skills are not pre-planned, then situations occur such as at one school where the same plants investigation was happening in multiple year groups. This might not have been an issue. If different skills are being developed, sometimes it's a lovely thing to do to see progression across the whole school. But this was not the case, as the children were even recording their observations in the same way. Bar charts across the whole school. When you look at the requirements for working scientifically, there are a number of generic science inquiry skills common across the entire primary school age. Asking questions, observing and measuring, planning different inquiries, performing tests, using equipment, identifying and classifying, gathering and recording data, and reporting, presenting and communicating data and findings. Looking carefully at the statutory requirements of the working scientifically aspects of the English national curriculum, it's possible to see how each skill is described for each age group and how they progress as the children move through the primary school. It's important that you as teachers understand this progression of skills to enable you to plan effective science lessons for your children. CIEC, the Centre for Industry Education Collaboration, have put together a very helpful document that sets out in grid format the progression of science skills from EYFS, age 4, to Key Stage 3, age 11 to 14. This can be very helpful to identify where the children in your class should be working. They have also made some excellent posters that separate these statements into child speak and into age phases. These could potentially then be displayed in either the classroom or your children's books to be used by you to highlight skills to focus on, or ones your children have mastered, or potentially as a target for your children so they know how to work as a scientist. An excellent feature of these posters is that statements that reflect the same skill are in a similar position on each of the posters. For example, questioning is at the top on each poster. This helps you and the children to keep track of which skills they are practicing. Opportunities for children to practice these skills should be given whenever possible. If you've assessed your class and the children are finding a particular skill tricky, then I would suggest practicing this in as many different contexts as possible. For example, if they find choosing correct equipment for their inquiries challenging, then give them lots of short opportunities to practice this outside of complete inquiries. Perhaps as part of a maths lesson on capacity. Which measuring cylinder for measuring an egg cupful, a mugful or a litre? Or as part of your design and technology lesson. Oh, I've made a mistake when I was adding my ingredients. Which sieve could I use for separating the flour and oats to make my biscuits? We should also be working to develop our children's vocabulary to support them in their talk and reporting. If a child has the words to explain their thinking, then they're able to talk more fluently about what they've discovered and take their learning forward. By upper Key Stage 2, age 11, children should be a lot more independent, and if we've worked to develop their inquiry skills carefully, they will be able to ask and answer their own increasingly more complex questions with less support from you, the teacher.
What do we think now?
We think we're making a boat and the wind resistance, and we'll use this to push it along.
How are we going to push it along? You said we think we've got a boat. It's something to do with wind resistance. We're going to use that to push it along. But what else do we need? You said there's something else.
A sail. And paper. We can cut it out of paper.
It can.
And then when we start blowing, it's going to be timed. Yeah.
Okay, times what?
And what is the looks like? It stays the same strength.
How are we going to measure how strong it is? Time it for what?
See how far it takes to get from one side to the other.
Maybe.
Yeah, that is.
Now, I've put a little title at the start of that sheet. What's the title at the start of that sheet for me? Josh, give that title a little read, just underneath the date.
Investigating what affects wind resistance.
What?
Affects.
Good. We're investigating what affects wind resistance. And most of you are absolutely right. We're going to do something with the boat. We're going to do something with the sail. We're going to time it with the stopwatch. I'm not trying to give too much away here. What affects this force of wind resistance, okay? That's what we're trying to do today. Now, we're going to plan this first of all. Before we can do anything, we need to get a good plan in place. So, what are all the possible things that we could or could be changed in your minds with this experiment? You know that we've got a guttering. We know that we're going to get a boat from one end to another. You know that we've got to do something with the sail. What is one thing that you think we could possibly change as we're going to start testing? Write it on your post-it note and then stick it in one of those yellow boxes, and we'll have a listen to some of the ideas that we get down. So anything that we could change when we go downstairs later on. How much water is in the pipe? Okay, nice. Put that on there. Spot on.
We could like cut like the paper into like a wind thing and then pop it on there.
Okay, so what are we changing there? Shapes for the sail?
Yeah.
So you're talking like triangles and circles, things like that? Well, no, keep it on there because we could change that. We could. That is a variable we could change. I'm not saying we are going to, but we could change it, couldn't we? What did you mean then? How big the sail is? Okay.
If it's smaller, it might not move as well. Or if it's
Prediction?
Because if it's bigger, more wind can hit it. Yeah, so it could move faster because there's more.
Are you confident? Are you 100% sure of that one?
Yeah. Maybe. Because if the sail is smaller, then it will go slower, and if it's bigger, then it will.
We're jumping ahead actually. We're jumping all the way down to the spot box here. We're having a bit of prediction.
Yeah.
But let's think of all the things that could change. Let's have a listen then. Kieran.
Length of the gutter.
Oh, nice. Yeah, we could change the length of the gutter. That could change easily. Length of the gutter. What else could we change? That's a good option, that one, Kieran. Brilliant. Something else. Something else. Nance.
Yeah, you could change the shape of the sail.
The shape of the sail.
How much water is in the pipe?
How much water is in the pipe? If there's no water in the pipe,
It won't move.
well, it might do. Depends how strong the wind is, surely. Any other variables? Isla.
The difference where we put the fan, so if we put it far away.
Nice. The distance of the fan. That's a very good one. What happens if it's going to go far away then? Talk on your tables. What's going to happen if the fan's further away or if it's closer?
It won't be as much. Like it won't be as much. It has less power. And it will spread the wind would spread out. It has less power when it's been. But if it's really close, it's coming straight for the fan. If it's further away, it has to
3,
travel.
2, 1. Gemma.
You could change the size of the sail.
Good. Change the size of the sail. So the size of the sail. Why is that different to the shape of the sail? What's different about that? Dan?
Because if the sail's bigger, then the wind off the fan will catch the sail.
What's different about the size and shape? What's different about those two words? I think some people, when they put down shape, might have thought size, but it's actually a very different meaning. Job?
Because the size, it could be small or large, but you could have a circle that's big or a circle that's small.
Good. Yeah, good. Circles, squares, and triangles, they're all different shapes. But size-wise, we'd keep it the same shape, but change the size of it. More. Charlie?
The direction of the fan.
Yeah, the direction of the fan. That's a good one. I hadn't thought of that one. Direction. Brilliant. Right, we'll come back to those in a minute. They're all of our variables. Now, we need to choose how many variables are we allowed in any test, really. If we're trying to keep it simple, if we're trying to keep it effective, how many variables do we want?
One.
Josh, say again?
One.
Good, yeah, we just want one, don't we? We want one variable, because otherwise we're trying to juggle ourselves over and looking, oh, we need to change that, but then we need to change that, and then go back to the other one. We just want one variable that we can change. On your tables now, using the blue post-it notes, can you think to yourself, what is one thing we could measure downstairs that will help us test the effects of wind resistance?
The sail?
Could measure the length of the sail. Is that going to answer our question? What's our question again? That we are investigating what affects wind resistance. Is the length of the sail going to help us? But you know what? We could measure that. So get it down. Let's get it on our board because it's an option. You've spotted that we could measure that. Let's keep it. What else have we got over there? How far it goes. How far it goes. How far away the fan is. Okay. What have you got on your tables that could help you though? What else could you measure using some of the equipment on your tables?
What time? How big
So say that again.
What time?
What do you mean, what time what? What time it is?
No, what time it takes to get across.
Is that something we could measure?
Yeah.
Well, we need to get it on there because these are all the possibilities. We now need to choose one of these variables that we are definitely going to change. Only one. And we're going to choose one of these variables that we're definitely going to measure. Okay? Once we've chosen them, we can move them down here and we're going to create a question. What is the variable that we're going to change? What is the variable we are going to measure? If you've got them on your table, if you want to add any, pull them up and stick them down the bottom there.
We could change the size of the boat.
The
shape of the sail.
Yeah.
Shape of the sail.
We could change like the size and the shape of the sail.
That's two things.
It has to be one, shape or sail.
Shape. No,
Shape.
Size.
Yeah, shape.
Yeah. Like, could there be one like right up
What are
like
you going
this?
for
So
now?
it could be one like
No, that's what he said, isn't it?
There's two things.
I suppose it
There's
was.
two things. Size is one thing, shape is another. So you can have a small
I
circle
think
and a
we
big
should
circle.
do how
So you change the size
how long it
and
takes.
you've also changed the shape.
Is it that one?
How long it takes to get to the other side? How long it takes for you to get to the other side?
Change
Yeah.
what, what?
Yeah.
Could you?
We just said over there, we'll change the size and shape. How many things is that you're changing?
Two.
Changing two. You can only change one. So then Joe said, right, we'll change the shape. I said, that's fine, but then you have to keep the size the same. Joe, what were we just talking about? What term?
The size of the surface area.
Good, the surface area. If you're going to only change the shape, you have to keep the size exactly the same. So if I draw a circle here, let's say I did some very complicated maths to find that covers exactly 26 centimetres squared. Then when I draw a triangle, I've got to make sure that that area, again that's covered, is exactly 26 centimetres squared. And if I draw a rectangle, I've got to make sure it's exactly. If I draw a hexagon, it's got to be exactly. If I draw a pentagon, it's got to be exactly, Daisy? 26 centimetres squared. Because the size has got to stay the same. So if you want to change the shape, fine by me. But I hope you know how to measure the surface area of a circle. Carry on. I'll let you have food for thought.
How about the shape of the sail?
What are we on for?
The size of the
No,
sail.
because if it's the size,
Okay,
you can
so
only like do
we will change the size.
Because
then you can
do
medium.
Yeah, you can do medium, massive.
Okay?
But if
So
it's
what are we going to
mini,
measure? We're going to change the size of something.
Do massive, mini, tiny.
Yeah, but they'll have to be the same size, I think, size. Yeah, that makes sense.
Yeah.
If we change how big the sail is, what will happen to how long it takes? Does that make
it
sense?
could take longer or shorter.
Now, if you've moved them down, you should be able to finally now move them one more step down to that next box, and we should have generated a question. And the question should make sense. You might need to reword it slightly. If we change the size of the sail, the surface area of the sail, what will happen to how long the boat takes to get to the other side, or the time it takes the boat to get to the other side? There are two more things we need to do as good scientists, I'm afraid, until we get building. First one, the pink boxes at the bottom.
Our predictions are?
Our predictions. What is a prediction? Talk to the person next to you. What is a prediction?
A really good guess. Like, it's a really
Just a
good
guess.
guess.
Like just a guess.
Like, if I said to you 76
Nice, say that again.
yeah, you would give me a relatively good
It
prediction.
doesn't have to be good, just what you think's going to
Yeah, what you think is going to happen.
What you think.
Right, Josh, what do we predict?
The bigger the surface is,
Oh, nice. Good language.
the more wind's going to hit it, which make it further. But say
We're there, but we're only measuring how long it's going to take. We're not measuring how far it's going to go, so reword that a little bit. So you predict that the more surface area,
the quicker it'll take.
yes, the less time.
It has more to hit.
Oh, go on, say that.
Because it has more to hit, but if it's a smaller object, it has less to hit. So
Yeah, when we say less to hit, what was that technical vocab I was trying to get people to use before? Job was into that. Surface.
Area.
Good, the smaller the surface area, you're right. In one sense, as Harvey said, there's less of an area for the wind to be caught by. So we're hoping the larger it is, there's more chance it's going to be caught. And you predict it's going to take less time. Okay, I'm happy with that.
Because the wind will just like rush straight past it.
Yeah, if it's
But if it's big, more wind can hit.
Make sure that all fit.
Around here, Josh.
Make sure that all 5
I will. 5 centimetres for the
So I'll do it from the 0. Yeah, I'll do it from the 0.
That's big.
It isn't that big.
Quite big.
How do you do it? Oh, yes. Oh, yeah. And then it's 78 centimetres squared. Alright, 50 centimetres squared. Told you.
Then it's 90. It's 54.
Oh. I got it.
How are we attaching these to the boat? This is the last thing we need to do. Poke through with your pencil. And you've got to be careful you don't rip it. Bingo.